How you doing, guys? Welcome to another video. This is topic 1.3, how do we organise the elements, and in this one we look at the non-metals. Let's go. Alright, topic 1.3, how do we organise the elements, the non-metals? We look at the location of non-metals, we look at naming groups 17 and 18, and we look at some of the trends in the non-metals. So the learning outcomes, what you need to be able to do is you need to be able to recognise the halogens and noble gas, explain some of the properties, explain the reactivity of group 17 and group 18, state the number of valence electrons in the halogens and the noble gases, and state and explain the chemical reactivity of group 18. So non-metals, as the name suggests, are elements that don't display the same set of properties as the metals. Non-metals have a much larger range of melting and boiling points at room temperature, and quite a few of the non-metal gases are gases at room temperature. Bromine is actually a liquid at room temperature as well, and I've marked that in green. As far as the properties of non-metals concerned, there are only two groups, group 17 and group 18, which consist entirely of non-metals. That is the halogens, group 17, and the noble gases, group 18. They're the only ones that contain all non-metals. If we draw our staircase, which starts at boron and works its way down, remember that we have metals on the left and we have non-metals on the right. So everything to the right of the staircase is classified as a non-metal. Our non-metals contain things like oxygen, carbon, nitrogen, but we mustn't forget hydrogen, which is actually on the metals side of the periodic table, but it is in fact a non-metal. So don't forget to include that if a question asks you about a non-metal, because it could be talking about hydrogen. Okay, let's have a look at our first group, group 17, the halogens. Now group 17, it has a valence electrons with a number of 7. So every element in the halogens has 7 electrons in its outermost shell. We say that 8 is a very stable electron configuration. So something with 7 wants to gain 1 electron to form a stable outer shell with 8, an octet. So all of the halogens will want to gain 1 electron and form ions with a 1- charge. Their atomic radius, the size of the atoms, increases as we move down, and the most reactive element of the family is fluorine, so that is the first element in the series of halogens. That means that their reactivity increases as we go up the group, or the reactivity decreases as we go down. Fluorine is the most reactive in the halogens, whereas iodine is one of the least reactive. So you've got to be careful. Are we talking about up because it increases or down because it decreases? Now group 17 elements form what we call diatomic molecules, which means they exist as two atoms that are chemically bonded together. So for instance, fluorine, elemental fluorine, is F2. It contains 2 F atoms that are bonded together via a chemical bond. Chlorine is the same. It would have the formula Cl2. Bromine would have the formula Br2, and iodine would have the formula I2. They consist of 2 atoms of either of the halogen bonded together, and they will always come as a 2. They're diatomic. Now, as we look at that diagram, as we go down, the reactivity will start to decrease. The reactivity of the halogens decreases as we go down the group. Okay, group 18, the noble or inert gases. The noble or inert gases start with helium and make their way down to radon. Now they have 8 electrons in their outer shell, which we describe as being a full outer shell. They're extremely stable and their reactions are rare, but they also get bigger as we go down the group as well. So why are group 18 elements described as noble gases? Well, before they used to be called inert gases, and the word inert meant does not react. But in fact, we now know that these elements in group 18 will react or form compounds only in very special conditions. So noble means that they have a full outer shell. One of their properties is they all have 8 electrons in their valence or outer shell. They're no longer called inert because we do know that they can form compounds, just rarely, and that is not the true sense of the word. Inert means it wouldn't form any compounds, but it does. So now we refer to them as noble, being like noble or king of the elements, because we have 8 electrons in the outer shell. As we go down the group, we see some interesting properties. We would see that their size increases, so the radius of the atoms increases. Their density also increases. Now, density is how many atoms you can get in a certain volume. Now, the density means that the more dense you are, the heavier you are. So something like xenon has a very high density, which means it's like a lead balloon. If we had a balloon of xenon and dropped it, it would hit the floor and make a noise. Helium, you know, is a very light gas and it raises when we have a balloon. One of the things we might be asked to do is compare helium with the other noble gases. So helium is in period 1, and period 1 can only contain 2 electrons, whereas all of the other noble gases, I've been saying, have 8 electrons in their outer shell. So why is helium different? How can we compare it and contrast it? Well, in comparison to the noble gases, helium does have a full outer shell. It's just that the first shell can only contain 2 electrons, but it's full, so it does have a full outer shell. Helium displays many properties that are similar to the noble gases, i.e. it's very unreactive. It doesn't burn, it doesn't form very many compounds, so it is a very unreactive or inert atom. What are some of the differences? Well, the difference between helium and the other noble gases is helium only has 2 electrons in its outer shell, while the other noble gases have 8. So that's one of the differences. The similarities are that they behave the same, because remember, things in the same group have similar chemical and physical properties. Okay, we need to be able to explain some of the trends of the physical properties of just the halogens. So when we have a non-metal compound, we have only very weak attractions between other non-metal compounds. So if we're dealing with something like fluorine gas, the fluorine gas molecules are floating around individually, but between them there's very little interaction. They don't really have an interaction. They're not attracted to each other. They're just moving independently, moving throughout the container. So there's no attraction or very little attraction between the gas particles. So that means they will have very low melting and boiling points. So if we have a look at group 1, which I have there as well, we remember the trend that as we went down group 1, the melting point started to decrease. With the halogens though, we have the opposite trend. As we go down the halogens, the melting point increases. Now that's weird because they have very little interaction between each other. But in fact, the bigger the molecules get, the more the interaction between them. So the more protons and neutrons and electrons you put in there, the more likely it is to have a stronger interaction with another molecule. So something like iodine, that has more electrons and protons and neutrons, so there is a stronger attraction between one I2 molecule and another I2 molecule. Something like fluorine, which is just F2, has very little attraction to other F2 molecules, which is why it's a gas. So the stronger the attraction, the more likely it is to be a liquid, and even stronger, it will be a solid. With the state at SLC, SLC is described as standard lab conditions. So the state means, is it a solid, is it a liquid, or is it a gas? So fluorine has a very low melting point and a very low boiling point, which means that it will be a gas at room temperature. Chlorine, with a boiling point as -34, that's below what we would expect room temperature to be, it will be a gas. Bromine, though, has a boiling point of 59 degrees, so at standard lab conditions, this is likely to be a liquid. Iodine and antimony, well, they both have fairly high boiling points, so they will both be solids. So one of the properties of group 17 is they turn from gases when they're very small to solids. If we're asked to explain the trend in reactivity of group 17, we need to introduce this concept called electronegativity. Electronegativity is a measure of an atom's ability to attract an electron. Halogens have a very high electronegativity, and they're known as electrophiles. They want to eat electrons. They want electrons really, really badly. So fluorine has a very high electronegativity, which means it will grab electrons from wherever it can get them. And basically, the more reactive you are, the better you are at grabbing electrons. So fluorine is the most reactive of the group 17 halogens, whereas antimony would be the least reactive of the group 17 halogens. So just to go over the trend for the halogens, the melting point, well, it increases as we go down. The boiling point, well, that increases as we go down. But the reactivity, that decreases as we go down. Fluorine is the most reactive, antimony the least. Alright, topic 1.3, some top tips. Remember the names and remember the locations. Remember the trends in group 17 and 18, and make sure you practice explaining some of those trends. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe for more, and I'll see you next time.